Good afternoon, Mr. Basma. Good afternoon, everybody. So the jury gave me the honor to be president of your jury this afternoon. So I will briefly introduce your jury members. So Mrs. Lavinia Grosso, maître de conférence from University Paris-Nanterre. Professor Goran Limberg from KTH Sweden, who is a reviewer of your work. Mr. Adnan Obedi is invited, and he is from a Transdev Society. Then Mr. Charbel Mansour, from Associate Professor from Lebanese American University. So he's a co-supervisor with Professor Pascal Stabat from Paris University, Mines Paris Tech. And I am Rojdi Trigui from University Gustave Eiffel. So you have approximately 45 minutes to defend your PhD, and then we will come to the questions of the members. So the floor is yours.
Thank you very much, Professor. Thank you very much. So good afternoon again, everyone. Today I will be presenting and defending my thesis entitled Energy Management Strategies for Battery Electric Bus Fleet. The thesis is prepared at Université PSL, Mines Paris Tech in Paris, France. Okay. So to start with, the greenhouse gas emissions are continuously increasing over the past century, despite the numerous technological enhancements in the energy efficiency of systems. This is mainly driven by the increasing energy demand worldwide. The transportation sector itself contributes to almost 1/4 of these emissions, whereas the public transport sector in specific corresponds to 6% of these greenhouse gas emissions. In addition, there are growing air quality concerns in major European cities. And as more cities are banning diesel vehicles, as these vehicles correspond to almost more than 40% of the total nitrogen oxides, which is a very harmful gas, impacting air quality and resulting in premature death and reducing life expectancy. That being said, there is a need to implement cleaner transportation technologies. And this is where battery electric buses represent a very promising solution to replace the current diesel bus fleet, thanks to their superior environmental performance, mainly driven by their lower greenhouse gas emissions and zero tailpipe emissions as well. So there are many key players actually involved in the problem of deployment of battery electric buses. For example, there is the bus operator responsible for operating the BEV fleet. Also, the entire electricity market is included in this problem, such as electricity generation, transmission, and distribution as well. In addition, regulatory authorities are also concerned as they impose different constraints and regulations on other key players. So these different key players may have different objectives and constraints when it comes to the deployment of electric buses, and thus they may have different approaches to this problem. For example, bus operators are mainly concerned with minimizing the total cost of electric buses while maintaining a smooth operation. The electricity generators, transmitters, and distributors are mainly concerned with reducing the major infrastructural modifications that may result from deploying electric buses. And also regulatory authorities are concerned with introducing the most cost-effective solutions because mainly they finance these projects. The scope of this thesis actually covers the BEV deployment from the operator's perspective. Despite their environmental benefits, battery electric buses are still facing many challenges holding off their market penetration at a massive scale. Out of these challenges facing the bus operators, there is the range anxiety due to the limited bus driving range in comparison to other bus technologies. Also, the know-how of operation, how to operate these buses in order to avoid any disruption in schedule or interruption in the service. And schedule disruption is defined as the bus inability to stay punctual to its schedule during the day. And service interruption is actually defined as the bus inability to complete a certain trip due to lack of energy on board. In addition, the readiness of the electric grid is a main concern for bus operators, as the high additional power demand resulting from charging these buses might be a challenge as well. So the limited bus driving range is actually impacted by the battery size, as larger batteries with larger energy capacity will improve this driving range. And the know-how of operation and the readiness of the electric grid are actually impacted by the charging strategy, how to charge these buses and at what power levels. So that being said, the battery size directly impacts the driving range of the bus and also drives the battery cost. And the charging strategy directly impacts the bus operation and also drives the charging and infrastructure cost as well. Nowadays, there are some electric buses operating in France and worldwide as well. And there are mainly two approaches are being considered when it comes to the deployment of electric buses. So first, buses are equipped with very large batteries accompanied with overnight charging. Such an approach results in high battery costs due to the large batteries. In addition, such approach may increase the risk of service interruption because there isn't any possibility to charge during the day. However, the risk of service disruption is really low for the same reason. On the other hand, smaller batteries plus frequent day charging is another approach to deploy electric buses. Such approach results in low battery cost, but high infrastructure cost due to the need for multiple charging events during the day. The risk of schedule disruption is higher because we have multiple charging events. However, the risk of service interruption is lower because we can always charge these buses during operation. So that being said, the main research question we are trying to address in this thesis is how to deploy electric buses to overcome their challenges and exploit their environmental benefits. Or in other words, what is a good combination of battery sizing and the charging strategy to ease the deployment of electric buses? And to answer this research question, I introduce in this thesis a methodology to provide optimal battery sizing and charging strategy for electric bus fleet in order to minimize its total cost of ownership while maintaining a smooth operation without any schedule disruption or service interruption. This proposed methodology is actually composed of three main steps. In the first step, I will introduce a bus energy model and analysis. Second, the scope is expanded to consider a fleet of electric buses where the techno-economic assessment of different fleet configurations will be considered. And in the final step, I optimize the different design parameters and control variables. So for the first step, I will introduce the bus configuration first, followed by the modeling approach, validation, and the energy analysis. So battery electric buses are mainly powered using battery, being the main and only energy source and power source on board. The battery should supply the different energy systems with their electric energy needs, mainly the propulsion system, the HVAC system, and the auxiliaries. So across the recent literature, some studies have tried to analyze and model the energy performance of electric buses by providing some models that tackled only the propulsion system of electric buses. Other models considered only the HVAC system or a combination of propulsion and HVAC systems, whereas very few models, if any, considered the different auxiliaries encountered on board the bus. That's why there was a clear gap in the literature on developing a comprehensive bus energy model capable of providing a precise assessment of its energy needs and at any operating conditions. The main components of the bus are really modeled, including the battery first. So the battery is modeled as an electrothermal coupled model, where the electric model is a Rent equivalent circuit and the thermal model is a lumped thermal model. These two models communicate through heat generation, and the calculated parameters allow the estimation of the battery state of charge on any charging or discharging profiles. In addition, the battery thermal management system is a critical component here in this case. More insights will be highlighted on this system later on in this presentation. The choice of these modeling approaches was actually based on the fact that we would like to attain a good computation complexity, data requirement, and model accuracy trade-offs. And that's why we have chosen these modeling approaches for the battery. The first main energy consumer for on an electric bus is the propulsion system itself. So the propulsion system is mainly composed of an electric machine being the main propulsion unit and powered by the battery. The electric machine is modeled as lookup tables, constant efficiency maps, in addition to inertial components to capture the dynamic behavior of the electric machine. The transmission system is modeled at constant torque transmission efficiency, mainly a reduction gear and a final drive. As for the braking system, there are two modes of braking on board the bus. First, we can brake the bus using regenerative braking, where the electric machine acts as a generator and it recuperates part of the vehicle kinetic energy. And also we can use pneumatic braking or frictional brakings, and more insights on these will be discussed later in this presentation. The driver is modeled as a PID controller where it follows a predefined reference speed. A very important component is the torque control unit. So the torque control unit analyzes the driver torque demand, and it takes into account the battery state of charge and the electric machine physical constraints. In a way, it controls the electric machine torque and the pneumatic braking torque such that it always meets the driver torque demand. The second main energy system on board the bus is the HVAC system. And in order to be able to model the HVAC unit needs, we first need to assess the thermal load for an electric bus and the temperature of the bus cabin under any weather conditions. And for that, we adopt and develop a thermal model for a bus cabin composed of an array of walls, the internal masses, such as the seatings and the dashboard, and the passengers occupying the bus. So through the walls, different modes of heat transfer take place, mainly conduction through the wall, convection between the wall and the cabin, radiation between the wall and the internal mass, and solar transmission and absorption, in addition to the convection that takes place between internal mass and the interior of the cabin. Also, passenger sensible and latent heat rejection are also considered. Due to the frequent opening and closure of the bus doors, it was important to consider the different heat losses encountered during this operation. So heat transfer or heat losses through the doors are considered in this model. The HVAC system now is mainly composed of a heat pump, an air circulation system, and a BTMS, or a battery thermal management system. Actually, there are two heat pumps equipped in the bus to meet its high thermal needs. And these heat pumps operate on the simple reversible vapor compression cycle. A dedicated heat pump control unit controls the behavior of the different components, respecting their physical limitations and taking into account, most importantly, the external temperature and the number of passengers occupying the bus, which has a direct impact on the energy consumption of the heat pump. The air circulation system is mainly, its main goal is to ensure proper ventilation of the cabin interior. It is mainly composed of a set of dampers and fans. The BTMS considered in this study is active air cooling, battery thermal management strategy, using an evaporator and set of dampers and fans. A dedicated BTMS control unit controls the air flow rate into the battery cells by taking into account the battery external temperature and the battery temperature and the external temperature. So that being said, this is the thermal scheme of the bus, including the cabin, HVAC system, and the battery thermal management system. The final main energy consumer on board the bus is the different auxiliaries. And in heavy-duty vehicles, these auxiliaries are really significant. And they result in significant energy consumption. So first, there is the pneumatic auxiliaries. Mainly, there is an air compressor that supplies compressed air at almost 10 bars to operate the pneumatic braking system. There is the hydraulic auxiliaries, such as the steering pump and the suspension system. And finally, the electric auxiliaries, including doors, parking brakes, lights, and wipers. That being said, these different developed models are validated, and the energy consumption or power demand for these different subsystems is compared to similar studies reported in the literature through simulation, experimental analysis, and sometimes compared to reports provided by bus operators or manufacturers. The mean error for the total bus energy consumption was less than 3%. So after developing and validating the energy models, I can now introduce the energy analysis for a battery electric bus. To do that, I will comment on the energy performance for the different energy systems at different operating conditions. And to start with the propulsion system first, I show in this figure the energy consumption of the propulsion system measured in kilowatt hours per kilometer at different driving cycles. And these driving cycles are actually sorted in their ascending order of their average speeds. We can observe that for low average speeds, or in other words, for high levels of traffic congestion, the energy consumption of the propulsion system is really high. It could be almost 10 to 15% higher in comparison to normal operating conditions, so for speeds between 10 to 15 kilometers per hour. And this deterioration in the propulsion system energy efficiency at high levels of traffic conditions is mainly due to the deterioration of the electric machine efficiency at low speeds. As for the auxiliaries, similarly, their energy consumption is evaluated for different driving cycles, and we can observe a high discrepancy in the auxiliaries' energy consumption. But most importantly, we can observe that the auxiliaries' energy consumption could reach 6% of the propulsion system energy consumption, and that's why it was critical to consider them in this energy analysis. As for the HVAC unit, so the model is evaluated at different weather conditions, and I plot here the average power demand of the HVAC unit at different external temperatures, and this average power demand is calculated over an entire trip. We can observe that for extreme weather conditions, so for example, for temperatures below 0 degrees or above 35 degrees, the HVAC unit power demand is extremely high, and this raises actually concerns over the bus ability to fulfill these energy needs, as it will impact its driving range significantly. Finally, combining all these energy systems together, we can evaluate the total energy consumption of the bus. In this three-dimensional surface, I show on the vertical axis the energy consumption of the bus measured in kilowatt hours per kilometer, and on the XY plane, I show the average speed and the external temperature. So for normal operating conditions, for example, for temperatures between 10 to 20 degrees, or for average speeds between 15 to 25 kilometers per hour, the energy consumption of the bus is around 1.5 to 3 kilowatt hours per kilometer, which is pretty typical for 18-ton, 12-meter long bus. However, the problem is observed at extreme weather conditions, for example, extreme cold conditions at -10 or extreme hot at 40 degrees, or at extreme high levels of traffic conditions, for example, for speeds below 5 or below 10 kilometers per hour. The energy consumption of the bus at such conditions could be even more than doubled in comparison to its normal operating conditions, raising questions over the bus ability to complete its daily trips. So after conducting this analysis, we can have a preliminary idea on the bus energy needs, on the bus required battery sizing as function of these conditions, and on the bus charging needs as well. However, in order to be able to precisely evaluate the bus battery sizing and charging needs, we need to put this bus in operation under real-world dynamic conditions, because its energy consumption is highly affected by these conditions. In addition, we need to consider the schedule of these buses, because the schedule determines the available charging time slots during the day. And this brings me to the second step of this methodology, which is to expand the scope and consider a fleet of electric buses, where we consider a fleet energy model first, accompanied by an economic model and an operation model. And finally, I will present the different trade-offs between the total cost of ownership or the economic model and the operation of battery electric bus fleet. So mainly a fleet of electric buses is composed of many electric buses, obviously, the stop stations along the bus line, chargers, so some stop stations might be equipped with chargers and they serve as charging stations, terminal station and the depot, and they also these could be equipped with chargers and they could serve as charging stations as well. And also we consider the real-time and dynamic varying driving conditions, also the weather conditions and the passengers load inside the bus. So these different components interact among each other through two means of energy interaction. First, there is a passengers flow from the stop stations to the bus, which impact the bus energy consumption. Also, there is energy flow from the chargers to the buses, or in other words, the charging process of electric buses. In addition, the schedule of these buses, as I have mentioned earlier, dictates their available charging time slots during the day and impacts their charging pattern. A very important component to consider is the charging strategy, and this charging strategy actually controls the charging behavior of each bus during the day. It is really critical to define the charging strategy. A charging strategy is defined by answering these three main questions: when to charge, or the charging time; where to charge, the charging location; and what is the charging duration, the charging energy and power. So by developing such a detailed energy model for a battery electric bus fleet, we can thus evaluate different bus configuration or different combination of battery sizing and charging strategy to impact their economic and operational aspect as well. To do that, I present an economic model, and I use a total cost of ownership model to evaluate the economic performance of a certain configuration of a line or a fleet of electric buses. The TCO model is an approach widely used for such applications. So first, we consider the unit cost, including the bus acquisition cost and the battery cost, which is variable as function of the battery size and the battery cost as well. Also, the operating costs are considered, such as energy cost, demand charge cost, or the power cost of electricity, and the labor cost. Infrastructure costs, including chargers acquisition and construction cost, and the chargers costs are directly related to their maximum power or the size of the charger. The battery replacement costs due to aging are also considered, maintenance costs, and financial costs, as we're dealing with different cash flows during this project, in addition to the numerous inputs and the model parameterization. In addition, we introduce a fleet operation model in order to assess the system operability. It is something like a key performance indicator to assess the operability of a certain configuration of electric bus fleet. And to do that, we start for the currently defined KPIs, key performance indicators for diesel buses, which is reflected in this punctuality index. So, for example, if a bus is delayed by less than 5 minutes in relative to its scheduled departure time, it will still be assigned a 100% PI. If the delay is between 5 to 10 minutes, the PI is 50%, and if the delay is above 10 minutes, the PI is 0%. Based on this, since these norms are defined for diesel buses, service interruption isn't considered because we don't really encounter this problem for diesel buses. And in order to proceed and apply it for a fleet of electric buses, we will assume that if the bus service is interrupted during any trip, automatically a PI of 0% is assigned. So based on this punctuality index, the average annual punctuality index calculated based on this presented criteria, the operator has to pay a penalty if it doesn't actually respect the defined punctuality index goals. And sometimes if the operator overachieves, it gets a bonus. Our observations have showed that the penalty is actually negligible in comparison to other cost components. One reason might be is that these norms are developed for diesel buses at lower total cost of ownership, and that's why we didn't really have this significant impact. Nonetheless, it's still critical and important to consider this the punctuality of the buses, as it is a main constraint we should fulfill. That being said, I can now introduce some trade-offs between the economic and operational aspect of a certain electric bus fleet. And to do that, we consider different bus configuration or different battery sizing and charging strategy for a fleet of electric buses. And on this plot, I show on the vertical axis the total cost of ownership of these buses measured in euros per kilometers and the punctuality index in percent. So a punctuality index of 100% means that these buses are at least as good as diesel buses in terms of operation. So to start with, we consider different battery sizes. So these battery sizes ranges from 120 to 250 kilowatt hours, and each solid line in this curve corresponds to a fixed battery size. On the other hand, we also consider different maximum charging power, so ranging from 100 to 150 kilowatts, and a dashed line corresponds to a fixed maximum charging power. So we can observe that as the maximum allowable charging power decreases, or in other words, if we move down along these solid lines for a constant battery size, the total cost of ownership decreases thanks to a reduction in the infrastructure cost, battery replacement cost, and demand charge. However, the punctuality index decreases because we're witnessing more delays in charging at lower power. On the other hand, if we increase the battery size at a fixed maximum charging power, so if we move up along these dashed lines, the total cost of ownership increases trivially due to the higher battery size. In addition, the punctuality index increases because we're having first a lower charging frequency during the day thanks to the larger batteries equipped on board. That being said, so this figure is actually developed for depot day charging, so for a specific charging infrastructure. However, if we consider other infrastructures such as end-line charging or charging at both ends of the line, we observe a similar behavior. And if we also consider opportunity charging at some stop stations, the behavior is more or less the same with different sensitivity to the maximum charging power due to the different number of charging events. That being said, there is a need to find an optimal trade-off between the economic or the total cost of ownership of an electric bus fleet and its punctuality index or its operation by taking into account these different variables or design parameters such as the infrastructure, the battery sizing, and the charging strategy as well. This brings me to the third step of this methodology, where I introduce an optimization algorithm to minimize the total cost of ownership of electric buses by controlling these different control variables and design parameters. So this methodology is actually composed of two main steps. So before heading into that, so across the recent literature, actually many studies try to tackle the cost problem of battery electric buses. And most of these studies actually focus on a specific cost component, one or two cost components of the total cost of deployment of electric buses. For example, some focus on the operating cost exclusively. Others focus on the battery replacement cost or the capital cost of electric buses, and so on and so forth. So none of the studies considers the total cost of ownership in a comprehensive way. In addition, these studies mainly concerned with a single control variable or a single design parameter. However, based on the assessment that I have introduced earlier, we realized that all these design parameters, such as battery sizing and charging and infrastructure, and the charging strategy, all impact the total cost of ownership and the operation of the system. And that's why this is the main gap we're trying to fill in the literature in this methodology, as we're trying to provide an optimization algorithm capable of considering the comprehensive total cost of ownership of electric buses by considering the majority of the design parameters and control variables. So the framework of this algorithm is as follows. So we have two main steps in this optimization algorithm. First, in the first step, we optimize the dynamic variables, and in order to minimize the energy and battery replacement costs, as they are actually driven by these variables. So at this step, first we start by determining the bus operating conditions. Second, we calculate the energy consumption using our previously developed models. And finally, I use dynamic programming optimization algorithm to optimize these dynamic variables and minimize energy and battery replacement costs. And since the bus operating conditions actually vary during the day or even during the day and from one month to the other, it is critical to ensure the different months and their different operating conditions during the year. In addition, at this stage, the battery size, which is a static variable or a design parameter, is fixed. However, the battery size has a direct impact on the energy consumption of the bus because larger batteries will result in higher energy consumption due to their additional weight and cooling needs. So we do this optimization exercise for each possible battery size. Moreover, since the schedule of the buses impact their available charging time slots during the day and their energy consumption as well, it was essential to consider the different buses operating along this line. So we have three main optimization loops. The one is concerned with the different operating conditions at different months. The second is concerned with the different possible battery sizes. And finally, the third one is concerned with the different buses and their different schedules operating in the fleet. The output of this first optimization step is to provide the optimal charging power, energy, and location for each bus in the fleet at each possible battery size and for each month during the year. These outputs actually feed the second optimization step, where we optimize the static variables, in specific the battery size for each bus along the line, by minimizing the total cost of ownership. And for this sake, we use a genetic algorithm-based optimization routine. So a couple of words on these optimization routines considered in this study. So first, starting with dynamic programming, the main objective function, as I have mentioned, is to minimize the total energy and battery replacement costs, where the energy costs are mainly as function of the electricity tariffs imposed and the energy consumption or the charging needs of the buses. The battery replacement costs are mainly related to the battery capacity fade due to its aging and to the battery pack cost as well. The main control variables are the charging energy and the charging power of each bus in the fleet. And the main constraints are the state of charge of the battery that should be maintained between a minimum and the maximum as recommended by battery manufacturers, and the schedule of the buses, which should always be respected. So in this case, we are considering a 100% punctuality index. So the second step in this optimization was based on genetic algorithm. And in this step, we minimize the total cost of ownership, including the battery energy demand charge cost, infrastructure, and battery replacement costs, by controlling the battery size for each bus in the fleet. So that being said, in order to evaluate the potential of this proposed methodology, I introduced a case study for bus line 21 in Paris. This bus is mainly composed of 20 buses operating along the line. The driving conditions for these buses are collected. For example, here I show a typical velocity profile for this for a bus along this line. A one-way trip is 9.7 kilometers in length, and one depot serves as a terminal station for this line. The weather conditions are also considered. The 10-year average temperature and solar flux daily profiles are considered in this case for the different months during the year. The passengers' occupancy level inside the bus are also considered, and we do that by measuring the passenger flow to the different stop stations along the bus line. Also, the bus schedule, as I've mentioned, the schedule for each bus is considered, and in addition to some parameterization of the different models. And in specific, I'm really interested in showing some numbers here. So for example, the cost of the battery pack considered in this study is at 580 euros per kilowatt hour. And the electric energy tariff imposed are, for the case of Paris, is 17 cents per kilowatt hour during the day and 13 cents per kilowatt hour at night or after 11 p.m. So that being said, I can now move to introduce some results based on this presented case study. So the results are actually split into three main parts. First, I will introduce the optimal design parameters resulted from this methodology. Second, I will highlight the optimal charging strategy or dynamic variables. And finally, I will comment on the total cost of ownership and its behavior. So to start with the optimal design parameters first, these parameters are the battery size. So first, we have, I show here in this figure, the optimal battery size for each bus operating along this line. And we can observe a discrepancy in the optimal battery sizes. However, the majority of the optimal battery sizes are around between 90 to 100 kilowatt hours. This discrepancy in the battery size is actually related to the different schedules of these buses and the different energy consumption of these buses, as some buses do more trips during the day in comparison to other buses. Another important component in the design considered is the charging infrastructure. And in this case, I plot the required number of chargers and their location in addition to their maximum charging power. So the optimization algorithm results show that we need 20 chargers at the depot, and their power ranges from 65 to 95 kilowatts, 7 at the terminal station, where their power ranges from 100 to 115 kilowatts. The second main outcome of this methodology is the optimal charging strategy or optimal dynamic variables. And as I have mentioned earlier, the charging strategy of a certain bus is directly linked to the adopted battery size. And for this sake, I am showing as an example, the optimal charging power profile for a certain bus operating along the line during the month of January exclusively, because for each month we have a different optimal, and for a 600 kilowatt hour battery size. So we can observe that most of the charging is taking place at night and at very high power, just to benefit from the low electricity tariffs imposed at night. and minimal charging is taking place during the day. For smaller battery sizes, actually, we observe the following. The less charging is taking place at night and at lower power, whereas more charging takes place during the day at higher power and at higher frequency as well. If we consider the smallest possible battery size, we observe that at night we have minimal amount of charging energy and at very low power. And during the day, there is a very high frequency of very high number of charging events at high power. And sometimes we need to charge at the stop stations, and this we didn't actually encounter for the other battery sizes, for the larger batteries. So that being said, as the battery size decreases in this case, charging frequency is increasing in general. The charging power during the day also increases, and the charging power overnight decreases. In order to be able to comment on these optimal results, we need to understand the behavior of the total cost of ownership as function of these different variables. And to do that, I show here in this figure, I plot the total cost of ownership at different battery sizes. And just to simplify the presentation, we are going to assume in this case that all buses along the line are equipped with the same battery size, mainly because sometimes bus operators prefer to have a uniform battery size for these buses. And so let's assume we don't have the luxury to change the battery size per bus. So that being said, we can realize the following. The minimum total cost of ownership is observed at more or less medium battery sizes, ranging around 100 kilowatt hours. For smaller battery sizes, we have higher costs, and for larger battery sizes, the costs actually increases monotonically. However, if we consider that we can equip the buses along the line with different battery sizes, we could even achieve a lower minimum in this case. In order to analyze the behavior of the TCO at different battery sizes, we will have a look at the different cost components composing this TCO. And to start with, I will introduce first the unit cost. And in this figure, I show the unit cost at different battery sizes. So basically, as the battery size increases, the unit cost actually linearly increases. Mainly larger battery sizes incurs larger unit costs. The unit cost actually corresponds to 45 to 60% of the total cost of ownership in this study. The second cost component is the infrastructure cost. So again, I plot the infrastructure cost for different battery sizes. So for small battery sizes, we have a very high infrastructure cost. Then for medium battery sizes, this infrastructure cost is really low. And then after that, it increases for very large battery sizes. The infrastructure costs are actually driven by the total charges required power demand. For small batteries, we realize that we need frequent charging during the day and at high power, so thus yielding to a high infrastructure cost. And for large batteries, very large batteries, we realize also that we need chargers at high power during the night, which also increases the infrastructure cost. And that's why medium-sized batteries result in the minimum infrastructure cost in this case. Infrastructure costs, in the way they are defined in this study, could correspond to 5 to 15% of the total cost of ownership. As for the energy costs, we observe, if we have a look actually at the vertical axis in this figure, we can observe that there isn't really a huge discrepancy in the energy cost, and this is due to the fact that we optimize the energy cost in the first optimization step for each battery size, for each possible battery size. Nonetheless, we can still observe a certain trend that would help us in analyzing the behavior of the energy cost. So we can identify three main regions: one where the energy cost increases for small batteries, then decreases for medium-sized batteries, and afterward it slightly increases for very large batteries. This behavior is actually driven by the trade-off that takes place between the energy consumption or the additional energy consumption for very large batteries and the low-cost night charging for these large batteries. The energy cost could correspond to 10 to 15% of the total cost of ownership. The battery replacement costs are also considered in this case, and in this figure, similarly, we can identify two main regions: one where the battery replacement costs are increasing between small to medium battery sizes, and another one where the replacement cost is decreasing for larger batteries. So again, here we have a trade-off between the frequency of battery replacement due to aging and the cost of the battery pack itself. The replacement cost could correspond between 3 to 9% of the TCO. Finally, the demand charge cost component, or the power cost of electricity, is shown here in this figure, and we observe a monotonic or increase as far at different battery sizes. Well, despite the fact that smaller batteries are actually charged at higher power, however, larger batteries mainly are charged buses equipped with larger batteries are charged simultaneously during the night, and thus the cumulative charging power or the charging load is really higher for larger batteries for this specific case and based on the bus schedule. The demanded charge cost could contribute between 5 to 10% of the total cost of ownership. In addition, the maintenance costs are also considered and the labor cost as well. However, they aren't really impacted by the by the optimization algorithm or by the control variables we are considering. So from what I have presented, I recall that the optimal obtained battery size was around 100 kilowatt hour for medium battery sizes, accompanied with end-line charging. And we can realize that the low unit cost for these battery sizes and the low infrastructure cost as well, and the demanded charge cost as well, are driving the optimal solution or driving the algorithm to choose medium-sized batteries as the optimal solution, despite the slightly higher battery replacement cost and slightly higher energy cost in this case. So this brings me to the end of this presentation. So in conclusion, the main contribution of this thesis was to try to answer the topical research question of how to deploy battery electric buses and how to exploit their environmental benefits by overcoming their challenges. And to do that, we first introduced a comprehensive energy modeling and assessment for battery electric buses by considering their different energy needs and different energy systems, such as the propulsion, HVAC system, and the different auxiliaries encountered on board. In a way, we can really comment on the precise and complete energy consumption of these buses. We have also considered the different operating conditions, such as weather conditions, driving conditions, and passengers' occupancy inside the bus. In a way, we can analyze the comprehensive energy performance of the bus at these conditions. And this is actually the first main contribution of this thesis. Then we expanded the scope to consider a fleet of electric buses. And to do that, we have considered many electric buses operating along the line, the charging station, stop station, depot, and terminal stations, and most importantly, the bus schedule. And this detailed techno-economic analysis based on the total cost of ownership and the system operability at different fleet configurations and different design parameters and control variables is actually the second main contribution of this thesis. Finally, I introduce a generalizable and comprehensive cost optimization to minimize the total cost of ownership of electric buses by optimally controlling its design parameters and control variables. And to do that, we have considered a comprehensive cost function in this case. And we have also tried to consider the majority of the design parameters and control variables. And also, most importantly, actually, we provide a generalizable methodology that could be applied to any bus fleet. And this is actually the third and final main contribution of this thesis. That being said, I can now move and introduce the possible future work and our perspective at the end of this thesis. The very first aspect to consider is the scheduling of these buses. I do believe we need to rethink the whole scheduling criteria for battery electric buses, because we have realized that the schedule of the bus has a direct impact on the choice of the optimal battery size, charging strategy, and charging infrastructure as well. So I believe it will be critical for battery electric buses to add this another dimension, which is the charging of electric buses when considering their scheduling. Also, it will be critical to assess the flexibility of the adopted optimal charging strategies and battery sizing. Simply, we're dealing with theoretical optimization algorithms under also theoretical conditions. However, it will be necessary to consider real-life varying conditions, for example, by considering perturbations along the bus line that would result in some delays impacting its charging behavior. And this should be assessed as well. Then we are planning to expand the scope to consider a network of electric buses at a city or a country level. By doing that, we can have an idea on the total environmental benefits of deploying electric buses. In parallel, it would be important to assess the impact of these buses at this scale on the entire electricity market, and how would the electric utility grid be capable of hosting this high additional power demand. Finally, it will be interesting also to investigate the possibility of energy integration between electric buses and other energy systems, such as buildings or industrial sites, as the resulting synergies may result in lower cost of total cost of ownership for battery electric buses, and will ease the deployment of battery electric buses as well. That being said, this brings me to the end of this presentation, and thank you very much for your attention, and I think I'm ready to receive your questions.